Okay, so in our next lecture, we're going to talk about, you see the title here, the word test is something that you'll see several times now in the next couple of sessions, and this refers to the fact that we're going to, given a sequence or a series, better, is this series convergent? We will find tests that is the case or not. And I'll remind you, we have already one some test. Remember the geometric series, and there it depended on two elements, A and R, where R was the most important, and there the criterion was if R is less than 1, we have convergent, and then there's a formula, but let's not talk about that now. And if R in absolute value is bigger than 1 or equal to it, then we have divergence. Okay? So this is in a case of a test. This is a test for the geometric series. But today we will talk about, well, the first test is kind of a bit weird because it's divergence and we really want convergence. So it's kind of not really what we want, and therefore I'm not going to spend too much time on it, but it's important nonetheless to mention it. So what is the divergence test? What is that about? Well, so we have, the question is, given a series like that, let's start it from 1. If you, the test is this. Let me write it in the way the test is formulated. Let me write it down right away. So if, so the question is, what about this series, right? When is this series convergent or divergent? And the criterion is the divergence test. It says if the limit of these elements is not 0, anything else, then what happens is, if this limit is not 0, you means these numbers stay always a little bit bigger than a certain given number, and you try to add them all up. That's way too much, and therefore this will be divergent. So it's a condition. If this condition is met, then we get divergence. For instance, a simple example that we all know is if an is 1. That gives this, that's the series 1 plus 1 plus 1 plus 1 plus 1. And we know that this is divergent. And you see here, why? Because if I take the limit for n going to infinity from 1, that is just 1, which is not 0. So that explains why it's divergent. Let's look at a little bit more special, a little bit more complicated thing. Let's look at this series. N over 4n plus 2. Is this series convergent or not? Well, let's figure it out. Okay, so we have to calculate the limit. Limit for n going to infinity, n over 4n plus 2. If I plug in infinity, I get infinity over infinity, right? So it's an indeterminate form. I need to do something. What can we do? You would say L'Hopital, that's correct, that works. But there, last time I discussed when we took this limit that there are easier ways of dealing with so-called rational functions. These are polynomials divided by polynomial fractions of polynomials. And so the best thing to deal with it is divide everything by the highest degree term. That would be n here, right? And so if I do this, remember when it's divided by n, there's everything by n. So wrong would be say, oh, I can scratch out this and that's it. No, no, no. That is an invalid way of solving a limit because we're using wrong algebra, right? Okay, be careful with that. So what is left? If I do this, I get the limit for n going to infinity. Top is 1 and the bottom. This cancels out to be just 4 plus 2n. But now, if I plug in infinity again, this clearly goes to 0. And so I'm left with 1/4. But 1/4 is different from 0, and that's the only thing that matters. Once we have something different from 0, we get divergence. Okay, there are a couple more problems in the homeworks that I will assign, but basically it's about finding a limit. But it is, as I said, not very useful because it only goes one way. It only goes this way, right? And it only works if it's non-zero. In other words, if your limit is 0, you cannot. So if the limit of an is 0, you might ask, well, do I have convergence? And the answer is, we don't know yet. So we have to do something else. And I'll give an example later on. Okay, but let's move to a real convergence test, and this is the one in the second one here, integral test. And so this is about integrals. So, again, here we have our sequence. Let's start again, see this, let's start it again from 1, but we can start from any other number, remember? Okay, so in order for this test to work, there's some conditions that we need. And the conditions are, well, first of all, an actually should be given, well, I said normally an is given by a formula, but it has to be by a function. So f has to be a continuous function. Now the word continuous might scare you a little bit, but you should keep in mind that every function that we run into is a continuous function. So that really is not a big deal for us. But this is, be careful, just because you have a formula doesn't mean that you can do this. Remember, we had the alternating series that was given by this formula. That's a formula that works for the various values for n, but it doesn't work for values for x. This is not a function. I explained this last time, but I say it again, because its value at x is a half is undefined. So at x equals half, it is undefined, because what would it be? You would replace x by a half. That means you take a square root of -1, which doesn't exist, at least not in the real numbers. Okay, so not every time this is the case, but in case that we have there, then we can start applying this. But unfortunately, there are two more conditions. F has to be positive, which is easy to check. That's not really a big deal. But the next one is a little bit annoying. It has to be, decreasing. So going down, but positive. Now, technically we should check this whenever we apply this test, but we're going to ignore this. Because basically every function that we will run into will have this property, that it is decreasing, if provided the test works. If the test works, which I have not explained yet, then the function will be decreasing. The only exceptions are trigonometric functions like sine and cosine. But you just have to trust that the function that they ask you to do this test with are going to be of this case. So I'm going to put this between parentheses, meaning we should check it, but we are not. Okay, now what's the test actually say? Well, it's called integral test. So there's an integral going to come, okay? And what we're going to do is integrate the function. That's where it might be not easy, but it's a definite integral. In fact, it's an improper integral. And so we start from 1, so let's put the same 1 here. It's not really necessary, but it's just common sense to do that. And here, the same endpoint. But this means that this is an improper integral. Remember, we did this last time. And for improper integrals, there are two possibilities, right? So either this improper integral diverges or it converges. And now the thing is that they act the same. I'm going to write it this way and explain it what I mean. I mean to say this acts the same as this, meaning that if this one converges, then this converges. If this one diverges, so then these correspond. If this one diverges, well, then also this one diverges. So these two also correspond. So whatever this one does, the same holds there. Now, if it's a convergent integral, that means that you get a number here. But be careful, that number you get, the answer you get, is not necessarily the value of the series. In fact, it's almost never. Okay, let's see how this works. Let's start with a series that is going to be very important for us. I'll write it up here. 1 1/2, 1/3, 1/4, 1/5, 1/6. You see the reciprocals of the numbers. And it's easiest if I start for 1, because then this is A1, this is A2, this is A3. Okay, and if you think this is a 1, you see that the index corresponds to the numerator. So we have an actually formula for that. An is just 1 over n. So the question is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus so on, convergent or not? Well, notice, by the way, that the limit of an for n going to infinity, that is, what is an? Well, an is just 1 over n, let's put it there. 1 over n, that is just 1 over infinity, is 0, right? So you say, oh, it's 0, so by the previous test, doesn't it mean that's convergent? No, remember, if the limit is 0, we don't know yet. And in fact, you'll see it's not going to be convergent. And for that, we're going to use the integral test. So the integral test. So what's the function that we're talking about? Well, this is the formula. The function is the same, right? The function is f of x is 1 over x. Okay, that's, by the way, positive, continuous, decreasing, so no problems there. So what we have to do, we have to calculate this integral. Now that's an improper integral, and the first thing always to do, if it's improper, is replace the improper endpoint by a proper endpoint, so t, and then we're gonna then we can apply the fundamental theorem of calculus. Okay, this is a very easy integral. The antiderivative of 1 over x is of course ln x, and this we plug in 1 and t. So plugging in, let's do the fundamental theorem of calculus. That is ln t minus ln of 1. Now ln of 1 is 0, but the issue is this guy. ln t, what is that? The ln of infinity is still infinity, because if you look at the logarithmic function, this is how it looks like. And so it does go to infinity here, meaning the improper integral diverges, right? That's the terminology that we had introduced here. And now we have the same conclusion. If the integral diverges, then the sum diverges. So conclusion, no, this is a divergent series. Okay, and notice the limit was 0, but it's still divergent. Okay, and that is, I'm not contradicting myself. Convince yourself of that. Okay, so that's an example of a divergent series. Well, let's look at one that is convergent. I'm going to give a few later on, but I want to do already a little bit harder problem. So the one I want to do is, let's look at this series. Summation ln n over n squared. And again, I'm going to start from 1. That makes it, otherwise from 0 would not even make sense, right? Okay. So we have a formula. So what we should do is integrate the corresponding integral. And again, if you want to really be sure, that you can check that this function that I circled here, it satisfies all these conditions here. It is continuous, it is positive, and it is, well, the hardest to see is decreasing, but you can make a graph of the function, you'll see that that is a decreasing function. Okay, so, right. But it is an improper integral, so these are the endpoints. So let's immediately write it as a limit. That's 1t. And then, since I have to integrate, it's easier to write here negative exponents. Okay, and this is not such an easy integral anymore. Anybody sees how to do that? Think about it yet? Pause the video if you don't know immediately and think about it. The answer is integration by parts, in other words, isolate. Because we have a logarithm here, that's the logarithm, that's the ln x, and then x minus 2, that is the algebraic part. And you know that this is a scale, that the top one is u and the bottom one is dv. Okay, let me, we have to do this definite integral, but for simplicity, for notation-wise, I'm just going to do first the indefinite integral. Because, especially with integration by parts, it's easier to do that separately. Okay, so we said that this should be the logarithm, which is ln x. I'll write it back here. U is ln x, and then this should be the algebraic part, so dv is x to the minus 2 dx. Remember, the dx is always part of that. Sorry, I even forgot to write it here now. Okay, and then by the formula for integration by parts, this is, oh no, what we need to calculate now is what is du. Well, take derivative, that's 1 over x dx. And what is v? That is, remember, antiderivative. So I have the antiderivatives, but power of antiderivative, add 1 to the exponent, divide by the exponent. Okay, well, if you want, this is minus x minus 1. Okay, so the formula is uv minus integral v du. So what is this now? Let's plug everything in. U and v, it's easier to write the v first. So we have this term, minus v du. so here the v and the u, 1 over x times minus x to the power minus 1 dx. Okay, minus and minus becomes a plus, so minus, let me rewrite this just now. The exponent in the negative exponent means in the denominator. The minus minus becomes a plus. And now what powers of x do I have? This is x to the minus 1, this is another x minus 1, so actually I have x to the power negative 2. If you multiply these two out. Remember, in these cases like this, you have to simplify things, okay? Now that's again easy, because that's the power rule, ln x over x. And the deriving is add 1 to the exponent divided by the exponent. Okay, and so if I would write it out nicely, we get this as an antiderivative plus c. Okay, so going back to our limit, the limit for t going to infinity, this function here, antiderivative now we have, that is minus ln x over x minus 1 over x, right? You see it? Same. And I have to plug in 1 and t. Okay, that's the limit for t going to infinity, minus ln t over t minus 1 over t minus, and now we plug in 1. ln of 1, the 0, so I get the 0 here, nothing important. And here if I plug in 1, I get a 1. Okie dokie. What about plugging infinity? Well, if I plug infinity, this clearly goes. That's a 0. That's because 1 over infinity is 0. But if I plug infinity here, I get infinity over infinity, because the ln of infinity is infinity and this is infinity. So this is again an indeterminate form. And if we have an indeterminate form, we should do something, perhaps L'Hopital. Yeah, so that get rid of everything. So this is the guy that I have to work out, and for that I'm going to use L'Hopital. Okay, I'm going to do this here. Oh no, let me erase this. I can erase this. You can always go back in the movie if you want to see what was there, right? Okay. So the limit here, we're gonna. So I'll write it separately, and then later we plug everything in. So minus ln t over t by L'Hopital. We're gonna take derivative of this guy. That is minus 1. Sorry, the whole thing is just first a limit, right? Let's forget not to write a limit. T going to infinity. We get the derivative is minus 1 over t. The derivative of this guy is just 1. And if I plug in infinity now, then I get. So now it's clear that also this goes to 0, right? This if I plug in infinity, and then the 1 in the denominator doesn't do anything. So the whole thing is 0. Now it doesn't matter what it is. It matters that it is a number. So this is 0, this is already 0, and this is minus 1. So in fact, we see that the full answer is 1. But as I said, that doesn't matter. What matters is this is convergent. And therefore, conclusion, this is convergent. Okay, so let me indicate that. Because this is convergent, I can conclude that this is convergent. But because this is 1, I cannot conclude that this is 1. That's the only thing that you have to be careful about. Okay, so this is our integral test. And again, there are going to be some homework problems. You see, it involves integration, it involves improper integrals, and therefore it involves limits. There's quite a lot of things that are used here. So if in case you have a problem with any of those, make sure that you catch up on that. And now finally, I want to do an application of this. And so I'll do this here. And this application is for so-called P-series. And this is going to be a type of series that's going to be important for us as well later on. And how they look like? Well, they look like this. Okay, let me explain. The P here is going to be some number. Just so it's a P of power. So it's a fixed power here, and it's the n that you have changed. So for instance, if P is 3, say, we would have the first one, A1 would be 1 over 3 to the power 1. A2 will be 1 over, sorry. No, what I'm saying. No, I say it wrong, right? Be very careful, yeah. Let's plug it in. If p is 3 and n is 1, then we have 1 to the power 3, that is just 1. What is a2? Well, that is 1. Now it's 2 to the power 3, that is 1/8. a3, it is now, my n is 3, so 3, and my p is still 3, to the power 3 is 1/27, and so on. So this is how these series look like. And the p stands for power, perhaps, but also for polynomial, because these really are polynomials. But notice, the strange way is we put the power of n in the denominator. Normally you do the opposite. You've been told you have to put it on top, but in this case we have to put it in the bottom. It's going to be important for when we apply it. But okay, so I'm going to apply the integral test to this guy. Now clearly that there is a function that describes this, and it's the function 1 over x to the power p, right? And this is decreasing, this is positive, so it satisfies all the things. So what I have to calculate is this improper integral. And so p, you might be thrown off by this p here, but p is just some number that I haven't told you what it is. It could be 2, it could be 7, it could be -3, even 2/3, but we just know it's some power. Okay, how we do this? Well, first of all, it's a limit. When you have proper integrals, always make them limits. Since I have to integrate, I like to write things in powers of x, not in the denominator. Okay, but that's a power of x, and that's easy. That's just a power rule, right? So limit to infinity. The power rule says, add 1 to the exponent. How do you do that if you don't know what p is? Well, you say it's just minus p plus 1. What else can you do? And then divide by that exponent. Okay, and that's between 1 and t. Great. So let's plug in what this means. If I plug in t, I get t to the power minus p plus 1 divided by minus p plus 1 minus, and now I plug in 1. If I plug in 1 in any power, that's always 1, so nothing happens here, and then the bottom is just whatever it is. Okay, so now I have to plug t inside here. Oh, you say any power infinity is infinity, right? Infinity to the power 3, that's infinity. Well, what about infinity to the power minus 2? Because if it's a negative exponent, then it actually means it goes, this would mean actually 1 over infinity squared, which would be 0. So it actually depends whether the power is positive or negative. Now we don't know. So we have to look at two cases. Case 1, let's look at the good case, namely, the good case is when it's negative, because then this would be 0, right? So if minus p plus 1 is less than 0, if it's negative, then this whole thing would be 0, and we have a value, this is the value, so it is convergent. What's the other case is, well, if this is a positive power, if minus p plus 1 is bigger than 0, then if I plug infinity, then it's going to give me infinity, so divergent. And remember, whatever this is, whatever this integral becomes, it's also the same what this series becomes. Right? This series here, this is the series that I was looking at. Okay, all right. So these are criteria. Let's work it out a little bit, what this means. So this is about this series, I repeated, there are two cases. If this is less than 0, but it's a bit hard to see, so perhaps easier if we bring the p to the other side, like do plus p. We can do that with inequalities as well, and then the condition becomes, this condition becomes 1 is less than p, right? If you want to say it otherwise, p bigger than 1. So I'm going to say it that way. If p is bigger than 1, then this series converges. Now, what's the other case? Well, do the same thing. We bring plus p on both sides, and now the condition becomes 1 is bigger than p, or perhaps easier to read, if p is smaller than 1, right? This is the same as that. You see that, right? Okay, so if p is less than 1, then this series is divergent. And that is what we call the p-series test. And so it's very simple. It just depends on what this power is. Now you might say, what about this one case you haven't actually mentioned, p equals 1. Now what does p equals 1 correspond to? Let's see. if we have 1 over n to the power p, and p is 1, well, that is just 1 over n, right? So we are talking about the series that we just had discussed here, one of our first examples, this one, and we figured out that this is divergent. Now, let me say something before we go back here. So it's a divergent series, means it's useless, right? It's infinity. And the strange thing is now that we still actually find it important enough to give it a name. So we're going to call this the harmonic series. Although it doesn't exist, it still has a name. Funny, no? Okay, so it's the harmonic series. Well, why is it called harmonic? I'm going to say 2 words about that, but it's not important. Just harmonic makes you think about harmony and therefore about music, right? And this is exactly what happens. See, if you hit a string on, say, a piano, if you hit a key, then it hits the string and the string starts vibrating and makes a sound. But because of vibrations, other strings are going to vibrate too. Now, not every other string is going to vibrate. Which other strings are going to vibrate? Strings that satisfy half the length of the original string, 1/3 of the length, 1/4 of the length, 1/5. Some strings, of course, are somewhere something else, proportions. But if you have these exact proportions here, those are going to vibrate. Now, another part of music theory is that if you take a string and you take half the length of this string, you get another tone. So, for instance, if you do this with C, I think you get a G. If you take 1/3, you get another tone that is derived from your original C. I think you probably get something like, I don't know these details of it, E or something like that. So you get, but a higher sounding E. So the smaller the string, the higher, of course, the sound is going to be. So what it means is that if you hit a string, hit a key, it makes this string, the corresponding string, vibrate, but also all the other strings at the same time are vibrating and making a noise. So what you hear is this total thing here. That's not good because it's infinity. So my ears are going to pop, right? If I hear everything here, yeah, my ears would pop. Luckily for us, our ears only catch us up to a certain hertz, and everything higher tones than that we cannot hear anymore. If you would have perfect hearing in that sense, you would hear everything, your ears would pop even if you hit one string, because everything starts vibrating and the whole thing would be infinitely big. You would have an infinite sound that I don't know what to think what that would mean. Okay, so that's the name harmonic series, but as I said, it's an important series that will come back later. So where does it fall? It's divergent, so it falls in the divergent case here. Let's go back. This divergent case. So in other words, I can add equal to 1 here as well. Well, that's it. So simple. Let's look at the example. Suppose we have this series here, n cubed over n to the 5th. Well, you should first simplify. You've got n squared, right? Remember, you might be inclined to put powers in upstairs, but for the p series, to see what it is, the power has to be written in the bottom. So n squared, what is this? 2 is bigger than 1, so this means it is convergent. Okay, let's look at a little bit, perhaps, different example. Let's say we have square root of n divided by n. Square root of n cubed divided by n to the 4th. Let's do this one. I should write this as a single power of n, but in the denominator. Well, let's write this first as a rational power. That would be 1/3, right? No. What am I saying? Gee. I'm getting tired, guys. It's a square root. That means a 2 in the denominator. It's a power 3, so it's a power 3/2. And in the bottom, we have n to the power 4. But I have to write this whole thing in the bottom, so I have to bring everything in the bottom. How do you bring powers from top to bottom? Bottom, top means changing the exponent. So in this case, we subtract. So n to the power 4 minus 3/2. That would be, let's see, that would be 8 minus 8/2 minus 3/2, so 5/2. So that would be summation 1 over n to the 5/2. What about 5/2? Well, it's bigger than 1, so it converges. Okay? But for instance, if you have something like this, 1 over square root of n, that would be summation 1 over n to the power, what's p here? Stop the video and figure it out for yourself. It's a half. And a half is less than 1, so divergent. And be very careful. convergent, divergent. 3 is bigger than 1, so convergent, right? No, no, no. We have to write it in the denominator, and that becomes -3, and -3 is less than 1, so it is divergent. So this is wrong. Okay, be very careful. It has to be written in the denominator. And so, yeah, you see, there are two cases here, right? This cases, and depending on what it is, your convergent, divergent. Now, this is something you're going to see often in this test. There are special cases, this bigger than 1, this, that, and so, and each is different. So be very careful to not get confused with them. I'm saying this because look at what we had for the geometric series. Geometric series, we had the absolute value of r had to be less than 1 to get convergent. In the P series, we have to just the opposite. P has to be bigger than 1 to convergent. So don't get confused there. All right, so there will be some homework problems that I will assign for this, and then, okay, and then we will go over these homework problems next time.